Okay, we're recording, and here's where we left off last time. We were talking about doing integrals in spherical coordinates, and a couple more examples I want to show you. Probably go through these relatively quickly because we've already seen a bunch of examples previously, but I think these are also useful. So here we start off with a domain being another ball, right? This one, though, centered on the y-axis. Previously, we've seen it centered on the z-axis or at the origin, which is, of course, the easy one. So this changes things pretty significantly because it really, in fact, spherical coordinates, if you think about it, is not a perfectly symmetric coordinate system, right? Z plays a special role. The phi angle is measured off of the z-axis. The theta angle measures around the z-axis. So there's an asymmetry there. Okay, first thing to make sure you do when you're any integral that you write down in spherical coordinates, step one, very first thing you write down is all of this, all together, all at the same time. Right? I can't emphasize enough. So easy to forget your stretching factor, and it's unavoidably a big deal to have the stretching factor in there. So again, write that down all at once. Then let's think about the bounds. And here's what slices look like, right? Theta slices look like this. They kind of, for the very first few values of theta, you're cutting just kind of a thin little, right? Just a little zest off the orange peel, right? And then as theta increases, it goes and you start to get more substantial slices, and they kind of go like that. And then there's a last slice over at the end. Right, so let's see here. The first slice is like this, where theta is equal to 0. And then the last slice, after kind of theta goes around, the last slice is sort of like this, in the negative x direction, where theta is pi. So there's your theta slicing process. How are we doing? Is everybody on board? Yeah. Notice, again, I've said this a million times, I'll say it a million more. Notice how important it is to have a picture on which to base that reasoning, right? And so having a qualitatively accurate, doesn't have to be beautiful. It needs to be a qualitatively accurate picture, indispensable in this slicing process. Okay, all right, now we focus on a given theta slice. Again, I like to redraw it over here off to the side, just so that I'm looking right at it. Angles look weird if you're looking askance at your cross section, right? So let's sort of redraw it there and think about the phi slices. Keep in mind, phi is this angle, right, measured at the origin from the positive part of the z-axis, right? And so these phi slices, I mean, the kind of the first barely there slice is going to happen when phi is equal to 0. And then we're going to get phi slices for all these various different values of phi. Right? In fact, just to be efficient, let me just say the phi slices kind of go along like this, and they go all the way over until they don't really quite disappear until you're straight down where phi is equal to pi. Yep, so 0 to pi. Everybody happy? Okay. And then for a given value of, so for a phi slice of our theta slice, and of course the phi slice of the theta slice is actually just this little segment. Rho starts at the origin, where rho is 0. Rho ends at this point up here, which is really this point over here, which is on your sphere. And the sphere has an equation that you can write down in rectangular coordinates using algebra, high school algebra, right? Based on a given radius, given center. Write down that equation, convert into spherical coordinates, and that gives you that which is your upper bound for rho. And I just skipped a bunch of algebra there, right? So you got to make sure that you're good with that algebra, conversion. First of all, writing down the equation of the sphere in the first place, and then converting into spherical coordinates, chapter 1 methods. Make sure you can do all that. Okay. All right. last example I want to show you here, this is more so an example about drawing than it is an example about slicing, really. Let me just dive in. So we've got this domain. Let's see what color I'm going to use. I'm going to use green. This is my domain. Kinda. It's a hard picture to draw. What it really is it's all of the yellow ball. All of that yellow ball that is outside of the blue ball. So think of, start with the yellow and then let this blue, imagine the blue kind of taking a big bite out of the bottom side of this yellow ball. And then what's left over, again, is what I have, whoops, I erased it by accident. What's left over is kind of this green thing there. But I have to acknowledge there's something really fundamentally wrong about this picture, right? It looks like I've kind of tunneled through and taken what you might call a cylindrical bite out. And that was not what happened. I took a spherical bite out. So in fact, let's not forget there's really kind of a lip going around like this. And so there's some solid here, then with an indentation sort of gap of air behind it, behind which there's more solid. How do you draw that? Right? That's hard to draw. I don't really have a good answer for how to draw that well. So nevertheless, there's our solid. How am I going to slice up something that I'm even having trouble drawing in the first place? And here's the big idea. The big idea is what I have written right here. You don't have to actually slice up the solid. You can slice up the components that go into defining the solid. Look at those individual slices and then work with those. So specifically, what I mean here is, let's think about this whole ball, right? Whole great big ball there. What is a theta slice of that great big ball? No problem. We're taking basically a planar slice. It's a half plane, right? Half planar slice out of a ball is going to give me a half a disc. No particular challenge there. So that's this thing right there. Nothing to it. And then, what I'm cutting out of it, I'm cutting out of it this green ball. What is the theta slice of that green ball? Well, it's another half disc, right? So it's all of that. And so in the same sense that what I struggle to draw here, my actual solid in question here, is blue, but subtract off all the green, right? Well, likewise, I don't need to draw the solid, understand the solid, slice up the solid. I can just do the same thing. Let's look at the blue here and subtract off the green. And so I get a pretty easy pitch that my theta slice actually looks about like that. Everybody happy? So I think it's a nice little artistic skill to have thought through. A lot easier to draw the slice of the solid than it is to draw the solid itself. How about that? Okay. Other details are analogous to examples we've already done, so I'm not going to spend a lot of time on it. I do want to point out we have a nice equilateral triangle situation here. Again, always be on the lookout for those. You never know when they're going to pop up. Again, these two edges are radii of that circle. And this edge is a radius of that circle. All of those radii we know are 1, and so this is an equilateral side length 1 triangle. So, good stuff. Okay. Real quick, let me remind you on the content syllabus, I broke up section 5.5 into 3 chunks because 5.5 is so huge, it's ridiculous, right? My goal, my optimistic but not in the bank goal for today is to actually finish 5.5 today, this being our 4th day working on section 5.5. right? So it's crazy. This third is actually not covered very much in the book. I think that's unfortunate. This is a really powerful idea, and it very naturally fits in with change of variables. I feel like it really ought to be discussed in this section. So this is all fair game. It is on the content syllabus. I'll remind you that there is a column in the content syllabus called included material, right? It's right next to the column called excluded material. And so this is the additional stuff that's in the lecture notes. It is fair game. It's part of the course. It's just not represented very much in the book. Okay. All right. So, as I often do, I'm going to start off talking about single variable calculus, partly to remind you of stuff to know from single variable, but mostly to set up a point of view that will extend naturally, conveniently, analogously, right, into the multivariable world. So here's the old fact I hope you've seen before. I hope you recall. In single variable calculus, this is what we call an odd function, and is so named because odd powers of x have this feature that a negative on the inside gives you a negative on the outside, right? Odd powers of x do this. Okay. But there's many other functions that do, but we call them all odd functions. Okay. This idea of a symmetric interval. What I mean by symmetric is that it's an interval that if you sort of reflect it over the origin, right? If you do like this, kind of rotate it around the origin, if you will, or you can think again. I like the concept of a reflection. If you just think of it as reflecting through the origin, that you get the same thing. It doesn't change at all. Right? So another way to say that is anytime you have a point in the interval, right, then its reflection, namely the negative of itself, also in the interval. And I think it's a pretty easy pitch that these are the same idea. Symmetric interval, another way to think of it is what I've got here, that whenever you have a point, the reflection of that point is also in the interval. Another way to think about this, and probably the way you saw it in your single variable class, was that the interval is from, for example, negative a to a, that these endpoints are negatives of each other. Those are all equivalent formulations. Okay, so that having been established, here's the big theorem. Big theorem is that if you have an odd function integrated over a symmetric domain, your integral is 0. Pretty great little theorem. Right? Does everybody remember this theorem, I hope? If not, it'd be a good thing to look up. I'm sure there's many resources available online if you haven't seen this before. I'm going to give you the real quick version of why this is true. Keep in mind an integral is a Riemann sum, and if you think about a Riemann sum added up over a symmetric interval, right? So from negative a to a, for example, right? Any term in that Riemann sum, such as that term there, corresponds to another term at the reflected point. That would be this term over here. And they have the same delta x's, but they have exact negative values of the function because of the oddness. Right? So because they have the exact negative values because of the oddness, these two terms, the green and the blue, you might say, terms in the Riemann sum, they cancel. And because of the symmetry, every term has a corresponding term to cancel with. And so everything cancels. We're left with nothing. It all disappears. And so that integral is 0. So it's kind of a Riemann sum point of view. And that's nice. As you all know, I'm a big fan of Riemann sum points of view. Let me show you arguably a slicker way to prove it, though, and that's using a substitution. This substitution right here, x equals negative u. And a quick reminder, substitutions are change of variables. That's kind of what we were modeling when we came up with change of variables in the first place. So here we go. because of the symmetry, an interval is its own reflection. So nothing happens if you replace I with g of I. Not a thing. Then I can do the pullback. It's a pullback because I start with an integral over an image, pull back through the substitution, change of variables function, by plugging in x equals g of u. Don't forget your stretching factor. That's a straight up change of variables. By the way, the stretching factor I claim is 1. Again, if you think about it, our change of variables function is a reflection. It's just x equals negative u, right? Nothing changes size when you just reflect. So nothing changes size, so stretching factor is 1. There's the pullback aspect of things. Then don't forget to plug in what g of u is. G of u is negative u. And then we can use the oddness of the function. Right? Well, I'll do it like this. Because of the oddness, this minus sign factors out. Okay, so what have we done? I've turned an integral into another integral. But in particular, my original integral is now the negative of itself. What could possibly equal to its own negative? Only 0. Right? So this integral, therefore, has to be 0. So, very quick, really, and all details, right there. So also a nice point of view on this single variable result. Okay, so we're going to now take all of that groundwork that we just laid in 1 dimension. We're going to step it up now to 2 dimensions. We're going to do all the same things, right? We talked about the minus sign, the reflection through the origin in 1 dimension. There is an analogous idea in 2 dimensions, and that is reflection over a line. Right? If you have a line in space, any line in space, you can talk about the reflection over that line. It's exactly what you think it is. If the line is the mirror, and if you're at X, then your image, your reflection in the mirror is where R of X is. Right? You might say that it's a location such that this line segment is perpendicularly bisected by the original line. Okay, so that's our 2-dimensional notion of a reflection. We can define odd symmetry in the exact analogous way. I can define a symmetric domain in the exact analogous way. It's if you have a point in a symmetric domain, its reflection must also be in that same domain. Said differently, it's a domain that when you reflect the whole domain, nothing changes, nothing happens. It remains the same domain. And with this set up, again, a complete analogy with the single variable result. Here's our new theorem that I'm going to show you how to prove. But here's the theorem. If you have an odd function integrated over a symmetric domain, your integral is 0. And this is a really nice theorem to have. You'd be surprised how often it is that you end up with integrals over symmetric domains with odd integrands. And so if that's the case, you don't have to slice and dice. You don't have to pick a coordinate system or remember a stretching factor. You don't have to compute anti-derivatives to plug in. Right? There's a tremendous amount of algebra you might save yourself. You just have to make the appropriate observations and celebrate that the integral is equal to 0. Awesome result. And I got a bunch of examples. Everybody with me so far? Everybody happy? Okay, 2 words of warning. Both conditions have to hold. So many students justifiably enthusiastic about symmetry because it's such a powerful result. We'll see a symmetric domain and forget to check that the function is odd. And then they claim symmetry when there is no actual symmetry argument, and you got nothing. So that's a dangerous thing. Make sure that you check both conditions. And I have a more precise list of requirements that's coming up. Furthermore, make sure you're using the same line. It's got to be the same line for both. Right? Makes sense. I mean, you'll see why in the picture in a minute, but the idea of a reflection necessary to define both of these has to be the same reflection. Okay. Alrighty. So, why is this true? 2 points of view. First of all, here's the change of variables point of view. I want to note how much the layout of what I've written here looks just like the layout of what we wrote here. I've got all the same ideas in exactly the same order. This is a morally equivalent argument here. It's just that it's two-dimensional instead of one-dimensional. And let's just walk through it real quick. We have a symmetric domain, so it is its own reflection. Nothing happens if you replace it with its own reflection. Same thing. Pull back. Right? We have an integral over an image. Pull back to the pre-image. Plug in the reflection. When you do a reflection, nothing changes size, so the stretching factor is 1. This is just a straight up pull back through the reflection. This minus sign comes out from the oddness of the function, right? The reflection on the inside gives you a minus sign on the outside, so that's the oddness kicking in. And then again, we have an integral equal to its own negative. That means that integral must be 0. Right? 0 being the only number that is its own negative. The exact same argument. Two-dimensional setting. Now, if you want to see a more geometric, sort of more visual point of view, here's a Riemann sum argument. Here is a domain. I did my best to draw something that's symmetric and yet not too specific, right? So I wanted something semi-random looking but still symmetric. It's harder than it looks. Anyway, so here's such a domain, symmetric over this line L. And the big idea is, because of the symmetry of the shape, any term in the Riemann sum, any little piece that you would chop it up into, well, there's a corresponding reflected piece. That's also in the domain because of the symmetry, right? And then furthermore, you get a minus sign on the value of the function because of the oddness of the integrand, right? Whenever you plug in a reflection, you get a minus sign. And so again, we have that this term in the summation and this term in the summation cancel with each other. Likewise for all other terms in the summation, every term corresponds to a piece that has a reflected piece that it cancels with. And so everything disappears and we're left with 0. Okay, so pick your favorite point of view on this, but that's why this theorem is true. Okay, diving in to get an example under our belts. Look at this integral right there. Pretty unattractive looking. Yeah, look at the integrand. Yikes. Right? So, looking pretty nasty. Look at our domain. Our domain is a region bounded by 2 curves. Well, with a little bit of a weird curve there. There's a quartic curve, but you do notice that both powers are even. You might have some instinct that this curve is itself actually symmetric. And it's not hard to argue. Let me draw a picture of it, though. Let's see here. So we'll look at... here's the XY axes, and look at this curve right here. Claim it looks something kind of like this. Roughly speaking, by the way, the x squared term dominates for small values of x, right? And then the x to the fourth, or more specifically the minus x to the fourth, dominates for larger values of x. So that's why it looks approximately like that. I hope that looks believable, familiar, some combination. Yeah. So anyway, that said, then we also have this curve. Let's see here. This curve here, which is like that. So our actual region D is this thing that's bounded in between. Like that. And doesn't it look symmetric? Right? So when you have a symmetric domain, I don't want to say that means that you should apply a symmetry argument, because that's an overstatement, right? But it's an eyebrow raiser. It should make you think, hey, there's a possibility. This might work. Conceivably, a symmetry argument might work out. It's worth thinking about investigating. Okay. All right. By the way, if you're unconvinced or unclear as to my argument, my claim that this curve is symmetric, here's a more explicit argument. When you reflect over the y-axis, you can write down an exact formula for what the reflection is. Right? If you have a point here, x comma y, when you reflect over that line, the reflection is negative x comma y. Now that's just a geometric appeal, right? You can see it's got the same y coordinate because we reflected, you might say horizontally, right? Same y coordinate, but the x coordinate's the negative here as it was there. And then you can take this formula for a reflection, you can plug the reflection directly into the equation, and what you find is that the reflection of that equation is exactly the same as the original equation. In other words, flipping that curve over this orange y-axis, nothing changes. So that's why that's symmetric. Okay. Alrighty. Okay. Let's talk now about the integrand itself. Our integrand is this function I'm going to write down here. Let's see here. Color choices. F of x comma y is all of this. There's our integrand. Right? So, it's going to turn out that this is an odd function. Specifically, it is odd over this line. It is odd, you might say then, through this reflection, by this reflection, however you want to say it. And the way we're going to see this is we're going to take this reflection, we're going to plug it right in to the function, right? And note that the function is going to just flat turn into its own negative, right? So f at the reflection, we've got some algebra to do to get there, but f of the reflection is the negative of the original value of the function. That's where that oddness is gonna show itself. Now let's be careful though about how we actually do this algebra that I just kind of shook a stick at. You've got to take your reflection. You've got to then plug in, as it says, this says that in the first position, namely wherever I see an x in this function, I've got to put negative x, because that's the reflection that I'm plugging into it. And so I get negative x up here where the x's were. Right? And then let's see here, I'll use yellow for the y's. I've got to plug in y everywhere I see a y up here. Conveniently, that's exactly, so in other words, don't do anything. So that's the process of plugging in to see what f of my reflection is. Now pausing, is everybody happy? Does everybody follow what I did there? Right? Got a formula for my reflection. Got to plug that in according to the formula for your integrand and see what you get. And then you have to do the corresponding algebra. So things to be careful about with the algebra. Let's see here. We've got a negative that's cubed. That gives me that minus sign right there. Right? Then I've also got here a negative that is squared. That just disappears. Then I've got over here, I've got a negative that I'm taking the sign of. And certain things you just have to remember about, classic known functions. Sine is an odd function. It's one of the many trig identities that y'all all memorized long ago back in high school. So that minus sign effectively pops out, cancels with that minus sign, thus leaving a plus. And notice then all together, when it's all said and done, this, right, is exactly the negative of, let's see here, let's see, I used blue. Oh, exactly the negative of that. So f at the reflection is exactly the negative of the original function. So it's odd. And we are done. We have an odd function integrated over a symmetric domain. Integral is equal to 0 by symmetry. We win. Didn't have to integrate anything. No substitutions, no integration by parts, no bounds, no corners, no spherical coordinates, polar coordinates, just a couple of quick observations. Done. Everybody with me? Everybody see how awesome and powerful that was? It was a big time saver. Really big time saver. Okay. So I am a huge fan of these theorems. I'm going to give you a little bit of background, my own personal experience with symmetry theorems. Again, in my past life as a college student, second major was in physics, and there's just a ton of math, specifically integrals, in a physics major, right? A lot of y'all are engineers. You're going to have a lot of integrals in your engineering major as well. My back of the envelope estimation, based on just memories of those days, is that about 20% of the integrals that I encountered were 0 by symmetry. And if you think about it, that's a ridiculous number of integrals. If 20%, I took 9 classes as part of my physics major, right? That means that ballpark 1.8 physics classes is how much work this one theorem saved me. Right? That's a lot of work. So I think it's a really big deal, and I hope you will use those theorems a lot. Now, you do have to give a complete argument. Here's what a complete argument entails. You got to tell me what your line of symmetry is. Remember, it's not about whether your answer is right. It's about whether your reasoning is valid reasoning. And this is a new material, so you have to actually give me the complete reasoning. By the way, a quick side note: the rules about what you have to tell me will change for the third midterm and for the final exam. I'll talk about that later. But for the moment, for the second midterm, which is a couple weeks away. I've lost track. It's not that. I'm sorry. When?
Next Monday. Isn't it the 31st? Oh.
Is it really?
Yeah.
Is it on Halloween?
Yeah.
Oh, wow. Scary. Okay, well, I guess I'd better start writing. Thanks for the reminder. Okay, coming up real soon then. You got to tell me the line of symmetry that you're using. Right? You've got to tell me what the formula is for the reflection through that line. And we'll talk about how to do that, mostly by examples. You have to note that the integrand is odd. After all, the theorem only works if the integrand is odd. So that's a big one to note. Here's the other thing. You got to demonstrate that the integrand is odd. It's usually not obvious. Look at how much algebra I had to do up here. This is non-trivial, right? To actually see that the integrand is indeed odd. So that you can't just kind of wave your hands at that. I need to see the algebra demonstrating the oddness. You also need the domain to be symmetric, and so you're going to have to make note of that. I, however, excuse you from demonstrating that the domain is symmetric. You got to state it. You got to be right. Right? But you don't have to prove it. And the reason why is that it's usually pretty clear just by kind of looking at the picture. And this is arguably one of the least clear examples. Usually when you do symmetry, it's almost a freebie that the domain is symmetric, if it is indeed symmetric. So no demonstration required, but you do have to state it. You have to note that the domain is symmetric, and it has to actually be symmetric. Okay, so these are the 5 requirements, and you got to give me all 5 of those for full credit. For whatever it's worth, if it were an exam question where either the question is about evaluating the integral, or maybe that's just part of the question. Let's just say that this was 10 points to evaluate that integral. Each one of these would be worth 2. So all 5 of these are comparably valuable. Not always exactly, but they're comparably valuable. So if you leave 1 or 2 of them off, you're throwing away points. So make sure to remember what the 5 requirements are, and make sure to document them clearly on your paper. By the way, so part of the reason that I want to see the complete argument, part of it, of course, is that's what this class is about. It's about reasoning, complete arguments. So that's what you got to get. That's what the class is. But for your possible convenience in other classes outside of Math 219. Maybe future engineering classes, they're probably going to go ahead and assume that you're proficient with multivariable calculus, if it's a prerequisite to the course. And they might be willing to be more flexible, and in fact I would imagine that they would be more flexible on what you demonstrate. So here's what I did many times as an undergrad. Physics exams tended to be long and tedious and arduous, right? And it happened on many occasions that I ran out of time. I wasn't finished. There was at least one integral left that I hadn't evaluated. And I got 15 seconds. I don't know, equals 0 by symmetry, right? And fold the book and turn it in. And I scored at least once. And I think I remember it was a couple of times that I actually got full credit for a guess, right? Now, I was very happy about that at the time. But was that just? No, not really, right? That was a guess. I got lucky, right? So there's 2 related notes then. One is, in this class, yeah, exactly. The integral equals 0 by symmetry, Hail Mary pass. Yeah, I'm aware of that, right? I know how that guess works, right? So you need to give me the 5 steps, if only to distinguish your work from someone who's just plain old guessing, right? Second related note, outside of this class, yeah, use that Hail Mary pass, by all means. I'm all for it. Go ahead, right? And who knows, you might score 2. Okay. All right. Last thing I'm going to comment before we do some more examples, do be careful. There is a real danger with symmetry arguments. Because if you do a symmetry argument and you make a mistake, you misunderstood the domain, and what you misunderstood to be the domain was symmetric, but the actual domain was not symmetric. Something like that, right? Maybe you write down the wrong formula for the reflection, and so you ended up incorrectly concluding the integrand is odd, when it isn't, right? The point is, all of your work on your page then is about a symmetry argument that doesn't exist. There is no valid symmetry argument. And that means that none of the work that you have on the page is progress toward a valid solution. And so, so you can end up with bad news, I'll call it, right? So, again, big fan. I hope you'll use symmetry arguments, but be careful. Take some of that massive amount of time and effort and inconvenience that you spared yourself by skipping, the integral itself, and double check, right? Double check, make triple sure that indeed all of these are actually working, because it's a very delicate, it's a very sensitive kind of argument, and anything goes wrong and it just doesn't work. Okay, so heads up. Okay, now here's an example. This is an example of what a student might submit sometime. The question is to compute this integral. The student correctly notes that the domain is symmetric. The student correctly notes that the integrand has an odd symmetry. And then from that and that alone, the student says, hey, the integral is 0 by symmetry. Well, let's look at the checklist. This student has, noted that the domain is symmetric, has noted that the integrand has odd symmetry, but the student has not told me what the line of symmetry is that they're using. Side note, this domain has several lines of symmetry. The integrand, that's a good. I can think of one symmetry that this integrand has, but I'm not sure. There might be others. I'm not sure. But certainly the student hasn't identified what line they're talking about. The student didn't give me the formula for the reflection. The student didn't demonstrate that the function is odd. There's 3 out of 5 gaps in this argument, right? So this student has done 40% of a valid argument. Everybody see the problem? Okay, so don't make that mistake. Okay, another example. Now this one is fully fleshed out, more than necessary, perhaps. We've got a domain right here. I'm going to leave it to y'all to think through that is what this domain is. And I'm going to point out just very quickly that there's a pretty easy, pretty believable line of symmetry there for that domain. Everybody see that? That line of symmetry, I argue, it's not hard to see how the reflection works. The idea is, let me zoom back in. In fact, I'll zoom in a little more. This reflection takes a point x comma y, which you can think of as related to this. I'm going to call it a kind of a rectangular frame. Think about these, this x arm, if you will, and this y arm, if you will. What's nice about this little rectangular frame is it's pretty easy to see how it reflects. That frame reflects. Let's see here, kind of like that. You know what? Let me do that in dark green. That'll be more visible. Yeah. So this piece reflects, the straight horizontal reflects the straight vertical, and this vertical reflects to horizontal. Right? And then you can kind of read off straight off of there that the reflection point here is negative y comma negative x. So geometric argument, and there's my reflection. How we doing? Okay. All right. Now there is you'll notice that there are some notes down here justifying why the domain is symmetric. Again, you don't have to do that. That's in there just in case anybody is unpersuaded by my picture. So you don't have to include any of that, but you do, again, have to actually include the statement, the true statement that the domain is symmetric. So there's that. Now we got to worry about the integrand. Is our integrand symmetric? And, here you go. Lots to plug in. This is my function, right? This is my f of x comma y. Keep in mind I'm plugging in the reflection, which is negative y comma x. That means, for example, everywhere up here that I see an x, notice that it's minus y that I'm plugging in to that first position. So everywhere up here that I see an x, I got to put minus y. Like so. And then likewise, everywhere up in the formula for f that I see a y, I'm plugging in minus x into that second position, into where I see y's. So all of these where I see y's, I've got to put minus x. Everybody okay with that? And everybody see the process? You got to be real careful with the plugging in there. But yeah. So, and then it's just a little bit of algebra, and interestingly, what happens is there's a minus sign in here, kind of a shared minus sign that gets raised to the 7th power, and that gives me a minus sign. Right? Let me zoom so we can see better. This shared, get rid of all this. There we go. This shared minus sign, 7th power, gives me a minus sign. Weirdly, over here, there's arguably shared minus signs there and there as well, but also the y and the x kind of traded position. So in fact, altogether, this is the same x minus y that I had in the original function. In some sense, nothing happens to this term here. This is just a wash. So notice you can't just assume that the exponents tell the whole story. Right? A lot of students would say, oh, well, this is odd and that's odd. They add up to 10, which is even, and would kind of, throw in the towel. Well, it adds up to even, right? But that's not the point. You got to plug in specifically the reflection, and only the 7, as it happens, actually matters here. And negative 1 to the 7th is negative, which is this minus, and so the function is odd, and so therefore this integral is 0 by symmetry. Right, so big nasty integral, weird domain that no matter how I sliced it would have corners, right? Lots of corner problems. 0 by symmetry. Everybody good? Okay. All right. Yeah. Now here's a dangerous one. You see a domain here. It's got certain corners. Oh, look at these two corners right here are clearly kind of flips of each other, right? And this, flipping over the y-axis. This is on the y-axis. This looks like a symmetric domain. We've got a symmetric domain. We've got an odd. Right, you can see it right there. We've got an odd function. And a lot of students would just at a glance think symmetric domain, odd function, integral 0 by symmetry. And again, this is a landmine. None of that's worth anything because there is no symmetry argument here. Critically, if you draw this domain, and let's do that real quick. If you draw this domain, the domain looks like this. And the only line of symmetry is the y-axis. But the oddness of the integrand only works if you replace y with negative y. If you think about what this reflection looks like, that would make this an odd function. I would need y to turn into negative y. I would need to reflect over the x-axis. These are not the same lines. Yes, you have oddness and symmetry, but over different lines, there is no symmetry argument. Does that make sense? So landmine, right? Dangerous. Very tempting to cite symmetry here. It does not work at all. So heads up. Okay. Last comment I'm going to make, and this is super quick. At 3 dimensions is exactly the same as 2 dimensions. It's just that you're reflecting through planes instead of through lines. But all the same corresponding ideas work. There is this idea of a function that has odd symmetry. Same deal. Reflections cause a minus sign. There is this idea of a domain being symmetric. Same concept, same exact idea. The domain is its own reflection, however you want to think about it. And we get this same result that I deliberately wrote to lay out on the page exactly the same because it's morally equivalent theorem. Odd integrand, symmetric domain, integral is 0. Just be sure that both conditions are satisfied. And be sure that you're using the same plane for each of those characteristics. So here's a quick example of odd symmetry working in 3 dimensions and nasty integral. Nasty. Right? Not because the integrand is hard, but look at the domain. The domain is a ball. That means that if you use rectangular coordinates, there's square roots everywhere. It's a nightmare. If you use spherical coordinates, smart move. Now you've got trig everywhere, right? And so this is going to be work to crank out this integral. So let's avoid that work We're going to reflect through the plane that is the XY plane. If you think about it, if you reflect through the XY plane, you get a minus sign on your Z coordinate, like that. Your domain is clearly symmetric through the plane. It's a ball. Balls are symmetric through like every plane going through the origin, right? The function is odd without too much trouble because this minus sign on the reflection, that minus sign gets cubed, which gives you the minus sign that you need for oddness, and we're done. Right? Symmetric domain, odd integrand, integral of 0 by symmetry. No trig, no square roots, no weird bounds, no rho squared sine phi, just 0. Everybody happy? Okay. All right, y'all have a good one. See you on Wednesday. And apparently don't forget about the exam on next Monday.